Okay, so what's the whole story about binomial? Well, the idea is, are we able to expand this to any power? That's the whole idea of this binomial expansion. So, well, we have a hint here. This guy, Pascal came up with a triangle that was named after his name as Pascal's triangle. Now, what Pascal was doing was he tried to see what could happen when n is 0 in this expansion. So you have a plus b to the power 0. Well, we all know it's 1. So you put a 1 there. And then you come and say, what about when n is 1? You have a plus b to the power 1, which is a plus b. So if you go for the coefficient of a is 1, the coefficient of b is also 1. So you place the first one there as a pivot, and then the other ones are coming on the sides. Okay, what about when n is 2? You know, we're having now a plus b to the power 2, which is actually a squared plus 2ab plus b squared. If we just go for the coefficients of these variables, the coefficient of a squared is 1 again. The coefficient of ab is 2. And the coefficient of b squared is 1. A simple observation could mean that it seems this one could also be obtained by adding this one plus the other one. We're not so sure. Let's see. What about when n is equal to 3? We'll have a plus b to the power 3, which will come out as a to the power 3 plus 3a squared b plus 3a b squared plus b power 3. If you do the expansion by hand, you do a plus b times a plus b, you get this one, and then times a plus b, you have the a plus b to the power 3. If you go for the coefficient, we have 1 for a to the power 3, we have 3 for a squared b, we have 3 for a b squared, and we have 1 for b3. Again, it looks like if you add these two, we're getting this one. If you add these two, we're getting this one. Okay. Then what about when n is equal to 4? Oh, that is a plus b to the power 4, which will give us a4 plus 4 a3b plus 6a2b2 plus 4ab3 plus b4. You pick the coefficients again. We have 1 for the first one, we have 4 for the second one, we have 6, we have 4, and we have 1. So like it always have that pattern. Like these numbers, they're repeating, these numbers, they're repeating, like that. And again, we see that if we add these two, we'll get this one. If we add these two, we'll get this one. If we add these two, we'll get this one. It seems like we can now stop the expansion and just build up from the Pascal's triangle. So if we go to the fifth line, we'll have 1 here. When we add these two, we'll get 5. We add these two, we'll get 10. We add these two, we'll get 10. We add these two, we'll get 5. And then we'll have 1 at the fifth. I mean, at the side number, yeah? Meaning that a plus b to the power 5 is a5 plus 5 a4 b plus 10 a3 b2 plus 10 a2 b3 plus 5 A, B, 4 plus B, 5. So meaning that this Pascal's here is giving us the coefficients. It's giving us the coefficients. Then what are we seeing? Well, look at the powers of A in the last line here. This was 5, 4, 3, 2, 1, 0. These are the powers of A. What about the powers of B? The powers of B were 0, 1, 2, 3, 4, 5 powers of B in the expansion. So it's easy to see that, oh, so every expansion will have the powers of A reducing, starting with the highest, which is the power of the initial expansion. And the powers of B will start from 0, spiking up to 5. But wow, can we use the Pascal's triangle for any setup? This setup looks like it's workable up to 5 or 6 or 7 if you're too fast. But what if we say A plus B, maybe up to the power 77? Imagine if you want to have the Pascal's, how would your the triangle, how many numbers do you need? How many lines do you need for you to get 77? So then this became a bit tricky. Okay. And then there was need now to find something that is simpler, that can be helping us get to n term. Maybe we don't need all the terms. Maybe just want to study what is happening at the 90th term. What is happening there? So we won't need the whole Pascal's triangle. Maybe we can drive some other ways. Okay. Now, for us to understand those ways, we need a bit of some terms that should come in. Then once we understand those terms, then be able to bring up the whole binomial expansion theorem. So, what terms do we need? Well, math is just like a language. So it's a language on its own, where if you hear someone telling you that 0 factorial, then you should be quick to know that they're talking about the number 1. Okay. Just like English, when they say count, somebody is calling you to go where they are. So in math, when you say 0 factorial, we mean 1. Okay. When we say 1 factorial, what do we mean? We mean multiply 1 by 0 factorial. Like that. Okay, so well, when we say 2 factorial, in math, we mean multiply 2 by 1 by 0 factorial, because you know what 0 factorial is. So 3 factorial, this is like 3 times 2 factorial. I'll stop at 2 because I know what 2 factorial is. From here, 2 factorial is 2. From here, 1 factorial is 1. So if I know what 2 factorial is, then 3 factorial will be as good as 3 times 2 factorial. I stop there because I know that this is just 3 times 2, which is 6. Okay, should they say 4 factorial? Well, I'll save my time by just saying 4 times 3 factorial because I know what this is. Okay, this is 6. So I have 24. Okay, what about 5 factorial? This is like 5 times 4 times 3 times 2 times 1 times 0 factorial. But why going all that far if you know that, if you know the value of 4 factorial? So if I know the value of 4 factorial, I'll just say 5 times 24. And I'll have the number. Okay? I'll have the number. If it is that much important to be found, you can always calculate those. So 24 by 5 giving us 120. Okay, so that if they say, well, what about 6 factorial? This is 6 times maybe 5 factorial, because we know what 5 factorial is. 5 factorial is 120. And then you multiply like that. So have 120 by 5, which is 600. So once you know the value of that factorial, then you are good at stopping that factorial and just bring it to the value and then calculate, multiply by the other number. Now, have you seen that as we go down, the whole idea is, well, if we had 10, we just want to say 10, because we don't know what 7 factorial is. We don't know what 8 factorial is. We don't know what 9 factorial. So we'll say 10 times 9 times 8 times 7 times 6. Well, 6 factorial. Maybe we can stop here because we know its value is 600. If we didn't know the value, then we go down up to 0 factorial. So if we keep going all the way up, maybe n factorial, where n is a whole number, then we'll say, oh, this can be written as n times n minus 1 times n minus 2 times n minus 3. You keep subtracting until you get to n minus n factorial. And understand this is just 0 factorial, which is 1. So, but we could also write n factorial as just n multiplied by n minus 1 factorial. You can end it in there, there's no problem. Okay? Hello.
6 times 120 is
7 twins, right?
yes, sir.
Right. I was thinking I can't make it again. Okay, then now, if we understand this, then we can move a bit to something that is a bit new also. Suppose you are given numbers 1, 2, 3, sitting like that. And then they ask, how many ways can you pick 2 numbers from 1 to 3? How many ways, or in other words, how many combinations are you able to make if you're getting two numbers? Well, this one we can do. So we'll have, maybe you can get 1, 1, 2, then you get 1, 3, then you get 2, 3. Well, if you say 2, 1, you mean the same thing. If you say 3, 1, you mean the same thing. If you say 3, 2, you mean the same thing. We're able to make 3 combinations there. You can get 2 numbers from 1 to 3 in 3 ways. Well, this we could do. Okay, what if we said 1, 2, 3, 4, 5? And we're doing the same. Okay, maybe now we increase, we go to 3 ways. So we'll have 1, 2, 3. We'll have 1, 3, 4. We'll have 1, 4, 5. We'll have 2, 3, 4. We'll have 2, 3, 5. We'll have 3, 4, 5. We'll have how many other combinations? I have 1, 2, 3, 4, 5, 6. There's 2 there. So maybe we can have 2, 4, 5. Yeah, 2, 4, 5. And maybe I can have 1, 3, 5. Yeah, 1, 3, 5. 2, 3, 5. 2, 4, 5. 3, 4, 5. I have 2, 4, 5 here. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, what about 1 to 5? So from here, 1, 4, 5, 1, 3, 5. Okay, 2, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. I feel there's one more. Who is able to see? 1, 2, 3, 1, 2, 4. 1 to 4. Do I have 1 to 4? No. Okay, so 1 to 4. Okay, I think there's no more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there should be 10. Okay. Maybe this we could do because the numbers are still small. What if they increase? They say 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then they ask you to pick in two twos. 1, 2, 1, 3. There are so many ways we can do that. Maybe we won't manage finding all of them. So what then could be the easiest way of us knowing how many combinations or how many ways you can pick two numbers from three numbers? So if we go back to this setup, this one, we have three numbers to pick from, and we are picking two numbers. Because that's how we write it mathematically. So we have three numbers, and we are picking two numbers. So to calculate this, we say, oh, 3 factorial on top, and then 2 factorial down, and then you do 3 minus 2 factorial. Let's see if we get 3. So we have 3 factorial over 2 factorial, and then 3 minus 2 is 1 factorial, but 1 factorial is just 1. Now 3 factorial can be written as 3 times 2 factorial. We end at 2 because 2 is also down here. 1 factorial is just 1. So that this 2 and this one will cancel, then we remain with 3. We got 3 for sure. What about this one? We had 1, 2, 3, 4, 5, and we're getting 1, 2, 3 at a time. So we had 5, 3. So this will be like 5 factorial, 3 factorial, and then 5 minus 3 factorial. So we have 5 factorial, 3 factorial, 2 factorial. So say 5 by 4 by 3 factorial. Why ending at 3? Because it's down here. So that one, no problem. Then the 2 will expand. So the 3 factorials will cancel. 2 here, 1, 2 there, 2. 5 by 2, 10 combinations. Oh, and we had them. So it means that if they give us so many terms and we cannot do the combination, we can still tell them how many times or how many ways you can combine those two numbers. Okay, how many ways you can pick, you can make the combinations there using binomial. So it's just trying to simplify our life. Okay, so what do we pick from this page? From this page, we pick that, well, if you're given any elements and they ask you to choose. Hello.
I haven't understood this.
Okay. Maybe when we do maybe 2 or 3 examples, it will make sense.
Okay.
Yeah. So we have any. So if you're taught like there are any elements, and then they ask you to be picking, So maybe I get back in this here, we had 3 numbers. Then they ask you to picking 2 numbers at a time. Then the question is, how many ways can you pick 2 numbers at a time from 3 numbers? You can't say I've picked 1 and 2 and I'm done. No, you could have also picked 1 and 3. You could have also picked 2 and 3. Now we're looking for those possible combinations that you could have made. Okay, so if there are 3 and you tell them, oh, you guys form groups of 2, 2. Oh, this one moves to the other. They could have also moved to the other person. Or they would have remained standing and these 2 would have moved. So we want to see such groupings that you can make. So if I have any of them, and I want to be making the groups of R size. Then you say, to know how many such groups can be made, you say n factorial, R factorial, and n minus R factorial, like that. Okay, so this is a general one now. For any numbers that I give. Okay, so if you got the table sheet now, you find that the whole question one can be used as an example here. Find the value of the following. A, 7, choose 4. By definition, we are saying this is 7 factorial over 4 factorial, and then 7 minus 4 factorial. Okay, which is 7 factorial over 4 factorial, and then what is 7 minus 4? We get 3 factorial, like that. Now we have to, every factorial, we have defined factorial. So we define factorial as reducing by one, all the way until you get the last number. Okay, or you can do 2 steps, just reduce by 1. You can do anything, as long as wherever you end, you put a factorial. That's how we have defined factorial. So when you're told 7 factorial, what does it mean? It means 7 by 6 by 5 by 4 factorial. You can keep going up to 0, but we'll end at 4 factorial because we have the same value 4 factorial down. So now we can work with the 3 factorial. Say 3 times 2 times 1. So that this 4 factorial that we haven't tampered with will help us take away that 4 factorial up there. Okay, this is 3 times 2, giving us 6. So this can cancel with that one. Then we'll remain with 7 times 5, which is 35. So here we're trying to understand how to use the factorial. We are trying to define factorial. And this is how we use factorial. Okay. Look at B.
Sir,
Hello.
so in terms of combinations, how do we explain that? Does it mean that we've got 7 elements, now we are picking in groups of 4, combinations of 4?
Now you're picking the combinations of 4.
So there are 35 possible outcomes.
There are 35 ways that you can pick 4 elements out of 7.
All right.
So let's say our elements were 1, 2, 3, 4, 5, 6, 7, is it? And then you are picking 4
Yes.
fours. So the first one could be 1, 2, 3, 4. The second, 1, 3, 4, 5. 1, 4, 5, 6. 1, 5, 6, 7. So you see that we still have so many. You come back and 2, 3, 4, 5. 2, 3, 5, 6, or 3, 6, 7. 2, 3, 5, 6. There are so many, but they are saying altogether there will be 35. So to use this method here, this is helping us not to start doing the combinations. We just want to know how many ways can we have those combinations? How many combinations can we have? So we can have 35 of them. And this is how we know. We use the formula. We don't combine manually. That is not easy. Okay. What about if you have 21 and they ask you to pick in groups of 19? How many ways can you do that? So you can do that 21 factorial over 19 factorial, and then 21 minus 19 factorial. So that you have 21 factorial over 19 factorial, then 21 minus 19, we get 2 factorial. So now we can reduce 21 by 20 by 19 factorial. Why? Because we have a 19 factorial down. Then the 2, we reduce it. So that this 19 and this one goes. Oh, we have 2 times 1. 2 here, 1, 2 there, 10. 10, 1 times 10, that is 210. So you can't tell me that you can easily just do the combinations and count them. Then they are 210 and you are done. No. That's not an easy thing to do. So that's how you do that. Okay. What about C? You have 8, choose 3, plus 8, choose 4. So you first get this value, then add them. Okay. So I'm saying you get this value, then you get this one, and add them. Which is 8 factorial for the first value, 3 factorial, and then 8 minus 3 factorial, plus 8 factorial, 4 factorial, and then 8 minus 4 factorial, which is 8 factorial, 3 factorial, 8 minus 3, 5 factorial. So I'm doing this one. And then plus 8 factorial, 4 factorial, and 4 factorial. Okay, then now we reduce. So we have 8 times 7 times 6 up to 5 factorial. We'll stop there because we have a 5 factorial down, multiplied by 3, multiplied by 2, plus 8 by 7 by 6 by 5 by 4 factorial over 4 factorial by 4 by 3 by 2. So that this and this can go, this and this can go. Then 3 times 2 is 6, and this 6 will go. Here also 3 times 2 is 6, and this 6 will go. 4 here 1, 4 here 2. So that the first one is 8 times 7, that is 56, plus 2 times 5, that's 10 times 7, that's 70. Altogether we get 126. 126. But if you look at the tutorial sheet, we have theorem 3. Question 3. It has a proof there, which is saying, well, if you have n fixed and there's r down, plus n, and then you have r minus 1, this thing is the same thing as n plus 1, and then r down. So if you look at here, we have 8 as our n, 8 as our n, and then we have 4 from this one, and then 4 minus 1 is 3, so we have 4 minus 1 plus, meaning that this is the same thing as 8 plus 1 over 4 to be our r. So this is going to be 9 choose 4. So let's see if this makes sense. So what is 9 choose 4? This is 9 factorial over 4 factorial and then 9 minus 4 factorial, which is 9 factorial over 4 factorial. 9 minus 4, 5 factorial. So we have 9 times 8 times 7 times 6 times 5 factorial over 4 times 3 times 2 times 5 factorial. So this and this go. Yeah, it's 4 minus 1. Because 4 minus 1 is 3. And then 3 and 2, they'll take away 6. Then 4 reduce this guy to 2. So we have 9 times 2 times 7. That is 18 times 7, which is 126. So you could actually apply the theorem there if you knew it. So that's how we apply theorem. So I was just trying to make you understand that, wow, doing this is the same thing as using this theorem, which is not a big deal.
Sir, but where have you taken this 8, 4 minus 1?
The theorem says having these two adding is the same thing as just evaluating this one.
So can you do it without changing to numbers?
Here we haven't proved the theorem, we've just used it to help us get what this sum is. Okay. The theorem says this thing here is the same thing as this one. So when we look at this one, you see, oh, 8, 8. Oh, then 4. Then 4 minus 1, 3. Oh, so I can use the theorem. What does the theorem say? It says just add 8 plus 1 and then choose 4. 8 plus 1 is 9. And then choose 4. You get 126. If the other guy didn't know about it, then they will add. They will add. So then they will have this plus that. You'll be done. By the time they reach here, I'm sure you are done. As they are doing this, you are answering another question. That's what I was trying to do here. So what we've done in this video is that we've defined the factorial. We've talked about the Pascal's triangle, just giving us an idea that, oh, the whole binomial expansion is just about expanding a plus b to the power n. Like when n is 0, when n is 1, when n is 2, when n is 3, when n is 4, when n is 5. Or it can go as far as possible for as long as n is the whole number. In this case.
Sir, excuse me. I don't. What are we trying to solve for?
I don't get. Hello? I didn't get your question. Okay, we'll have you in your able to speak. So I was just trying to give a summary of what we've done here. Introduce the Pascal's triangle and the terms. Which terms? The factorial. Okay, factorial, we understand now what it is. And then, wow, even the issue of combination, the choose, we understand now what they are. And I've done examples on the Torah sheet to answer question 1, A, B, and C on the Torah sheet. So we are still coming back to understand a bit more of these terms by looking at what is on question 2, what is on question 3 in the Torah sheet, question 4, question 5, question 6, question 7, question 8, question 9. So it's like the Torah sheet is done, just what we have done here. So we're just coming to do a bit more and then there's nothing hard here. If we can cool down, I need to have my supper. So for 10 minutes, and then we'll join. So joining at this is 1918. So we'll join at 1930. So you keep time so that we go up to 2010. Let's get another class. So don't worry, keep your questions when you come back, you understand. This is a very simple thing to do.